So, the next thing we want to discuss about matrices is how to use matrices to solve a system of linear equations. Okay, and in this we will talk about Kramer's rule. Okay. So, what is a system of linear equations and where do matrices play a role in system of linear equations? So, suppose you have a system of linear equations, let us say you have unknowns are x, y and z. Okay. These are unknowns. Okay. And our equations, we have equations denoted by, let us say I will just call this a1x plus b1y plus c1z equal to d1, a2x plus b2y plus c2z equal to d2, a3x plus b3y plus c3z equal to d3, where a1, b1, c1, d1, a2, b2, c2, d2, a3, b3, c3, d3 are all scalars. Okay. They are all scalars, that means they can be real or they can be complex numbers. Okay. You can write this in the following form. This is exactly the same as writing a1, b1, c1, a2, b2, c2, a3, b3, c3 of this matrix multiplied by another matrix that has just one column. Okay, and that matrix is denoted by x, y, z. So, as I said, the rules for matrix multiplication, you multiply a1 by x, add b1 by y, add c1 by c1 with z, which is exactly this, and this is equal to d1. Similarly, if you do a2 into x, b2 into y, c2 into z, you will get d2. If you do a3x plus b3y plus c3z, you will get d3. And I can write a system of linear equations in matrix form, and you can do this for any number of equations. You can do this for any number of variables and any number of equations. So, for arbitrary number of equations and unknowns. Okay. Now, I said you can do it for arbitrary number of equations and unknowns, but you know very well that there are conditions when this system of linear equations can be solved. Okay. So, it can be done for arbitrary number of equations and unknowns, but solution for x, y, z can only be obtained for certain cases. That means, if you have this arbitrary number of if you have this system of equations, okay, then it is essential that I mean you would intuitively imagine that the number of equations should be equal to the number of unknowns. So, if you have 3 unknowns and you have 3 equations, then you can solve and you can get a unique value of the unknowns. Okay, and that's what you expect. Okay, there are more there can be more I would say complicated cases. Okay, this is in general you expect that, but we'll see later that if these equations are linearly dependent, okay, then it turns out that 3 equations cannot solve for 3 unknowns. Okay, so actually in order to see when this can be solved, you need to get the idea of something called a rank, which we will talk about later. But the basic point right here is that if you have a system of equations, okay, then you can represent it in matrix form. Okay. So, now let us say you have the case where so if 3 equations are linearly independent, and consistent, then we can solve for the 3 unknowns. So, I will come to what is meant by linearly independent and consistent in a few minutes, but let us assume that you can solve for the 3 unknowns. So, how would you imagine solving for the 3 unknowns? Okay. Now, there is one rule called the Kramer's rule, which can be used to solve for the 3 unknowns. Okay. And I will just mention this right here. Okay. So, again this is only in the cases when these equations are linearly independent and consistent. So, if they are linearly independent and consistent, okay, then I can write x as a ratio of determinants, okay. And what is that ratio of determinants? So, I will write the denominator first. So, denominator is a1 b1 c1 a2 b2 c2 a3 b3 c3, which is nothing but the set of these coefficients, which is nothing but the determinant of this matrix. Okay. Now, obviously the value of x should depend on also on d1, d2, d3. So, the numerator, okay, looks like d1 b1 c1 d2 b2 c2 d3 b3 c3. Okay. Similarly I can write y as, again you have the same denominator a1 b1 c1 a2 b2 c2 a3 b3 c3, but in the numerator what you have is a1 d1 c1 a2 d2 c2 a3 d3 c3. So, notice what you did, and similarly for z, okay, I won't I'll just write what is z. So, z is equal to a1 b1 d1 a2 b2 d2 a3 b3 d3 a1 b1 c1 a2 b2 c2 a3 b3 c3. Okay. So, what we did is we have this determinant of the matrix. So, that is the same so the denominator for x, y, z are the same. In the numerator, in the first case you replaced the first column with d1, d2, d3. In the case of y, you replace the second column with d1, d2, d3. In the case of z, you replace the third column with d1, d2, d3. Okay. So, this Kramer's rule can be used to quickly solve a system of linear equations, okay, provided, so works provided the equations are consistent and linearly independent. Okay. So, what that means is that the number of equations should be equal to the number of unknowns, and the equation should be internally consistent. Okay. So, that is the condition for this. Now, I'll just come back to this idea of what it means for the equations to be linearly independent and what it means for them to be consistent. Okay. So, again let me emphasize one more point, that the Kramer's rule that we have done, I have shown it for a 3 by 3 matrix. So, for 3 equations and 3 unknowns. You can do this for an n by n matrix, okay. For n equations and n unknowns, you can write exactly similar expressions, okay, and Kramer's rule will be valid in that case also. Only thing, in those cases your determinants will be much larger, okay, but Kramer's rule is still valid. Okay. So, now let's look at some equations that are linearly dependent, okay, or inconsistent. Okay. So, what does, so we said linearly independent and consistent. So, we said that only if the equations are linearly independent and consistent can we apply Kramer's rule. So, what would be an example of a case where the equations are not linearly independent, and what would be an example of a case where the equations are not consistent? Okay. So, let us take a simple example. So, suppose I have x plus y equal to 2 as my first equation. My second equation is 2x plus 2y equal to 4. Okay, so, I have two equations and two unknowns, two equations and two unknowns. However, can you solve for x and y? The answer is no, you cannot solve for x and y. So, cannot solve for x and y because second equation is same as first equation. Okay. So, second equation is the same as first equation. If you just divide by 2, so as first equation multiplied by 2. Okay. This is a simple example I did for two equations and two unknowns. If you have three equations and three unknowns, then it is important you look whether one equation, whether one of these one of the left hand in the left hand side, one of the terms can be written as a linear combination of the other two. Okay. For example, let us take x plus y plus z equal to 3, okay, and let us take another equation that looks like 2x plus 3y plus z equal to, make it 5. Okay. Now, the third equation I will make it as 4x plus 5y plus 3z equal to 11. Okay, now I have three equations and three unknowns, but notice that if I call this 1, 2 and 3, we notice that 3 equal to 2 plus 2 times 1. So, 4x is 2x plus 2 times x, 5y is 3y plus 2 times y, 3z is z plus 2 times z, 11 is 5 plus 2 times 3. Okay. So, the third equation is nothing but the second equation plus 2 times the first equation. So, this implies that these equations are not linearly independent. So, you cannot solve using Kramer's rule for this system. In fact what you will get is that the determinant will turn out to be 0. Okay. In fact what you will get is that your determinant of this matrix. So, if you take 1 1 1 2 3 1 4 5 3, this determinant equal to 0. You can verify this. Okay. You can easily verify that this goes to 0. So, Kramer's rule does not work. Okay. And you cannot solve this system of equations, and it is obvious because you do not really have 3 independent equations. You have only 2 independent equations and you have 3 unknowns. So, you cannot solve it. Okay. Now, what about the idea of consistency? And I will just do it in this part. So, now suppose you have an equation, let us say x plus y equal to 2, 2x plus 2y equal to 5. You look at them, there are two equations, but you notice that the left hand side of the second equation is twice the left hand side of first equation, but the right hand side of the second equation is not twice the right hand side of the first equation. So, left hand side of second equation equal to twice into left hand side of first equation, but right hand side of second equation is not equal to twice right hand side of first equation. Okay. In this case, the equations are said to be inconsistent. That means if I just take the first equation multiply by 2, I will get 2x plus 2y equal to 4, but here I have 2x plus 2y equal to 5. So, there is no solution. So, these equations do not make sense or they are inconsistent. Okay. So, clearly you can apply Kramer's, you cannot apply Kramer's rule, you cannot solve this system of equations. And I showed this for a 2 by 2 system, but you can extend for other systems also. Okay. So, it is important that before you try to solve the equations, you verify, before you try to solve a system of equations, you should verify that they are both linearly independent and consistent. Okay. Only then you can use this Kramer's rule. Okay. Now, you can solve a system of equations using row operations. Okay. You do not need to use Kramer's rule, you can actually use row operations. So how would you do this? Okay. So, I'll show this with an example, okay, and then you can do it for specific cases. So let's just take one of the examples that we had. So, suppose I take equal to 2 and I take 3x plus 2y plus z equal to let us say 5, and I take let us say I take x minus y plus 0 times z, x minus y I want it as 1. Okay. So, suppose I take this system of equations. Okay. Now, you can solve for x, y, z. So, what you can do is if you solve for x, y, z, what you will get is let us just calculate the determinant. Okay. So, I will write this in the following form: 1 1 1 3 2 1 1 minus 1 0, this multiplied by x y z is equal to 2 5 1. I will do a row operation that converts this 3 to 0. So, what I will do is I will do I will do a row operation that does R2 minus 3 R1. So, what that will do is wherever I have R, I do 3 minus 3 times 1, that is 0. I will do 2 minus 3 times 1, I will get minus 1, and I will do 1 minus 3 times 1, I will get minus 2. Okay. So, and in addition what I will do is R3 minus R1. So, I will do these two operations and it will be instantly clear why I am doing this. So, what I will get is 1 1 1, R1 is not changed, R2 you subtract 3 times R1. So, you will get 0, 2 minus 3 is minus 1, 1 minus 3 is minus 2, and R3 minus R1. So, I will get 0 minus 1 minus 1 minus 2, 0 minus 1 is minus 1. Okay. So, I did this on the left hand side, I have to do the same thing on the right hand side. So, what I will do is I will leave the 2 as it is. Now, 5 minus 3 times 2 is minus 1, 1 minus 2 is minus 1. So, I get this equation. So, what I did is I just did some subtraction of the equations, okay, and I got this. Now, notice that I have two zeros here. Okay. What I will do is I will try to get a 0 here by subtracting this row. So, next what you do is I will do the following. So, I will do R3 minus 2 R2. Okay. So, if I do R3 minus 2 R2, you can see what happens. Okay. So, I will just show it right here. So, what I will get is 1 1 1, R1 is unchanged. Now, R2 is unchanged from here. So, 0 minus 1 minus 2. Now, R3 minus 2 R2. So, this 0 minus 2 times 0 is just still 0. So, that is important that I converted this to 0 first. So, this is not affected. Now, minus 2 times minus 1. So, minus 2 plus 2, that is 0, minus 1 plus 4, that is 3. Okay. This times x y z and this is equal to, now what I will have is 2 minus 1. Now, minus 1 minus 2 times minus 1, so plus 2, that is 1. Okay. So, you converted the equations to something like this. So, the same 3 equations you sort of did some linear combinations and you got this set of equations. Now, you can immediately see, just look at the third equation. So, the third equation says 3z equal to 1 implies z equal to 1 by 3. Okay, immediately you do not have to calculate any determinants. The second equation says minus y minus 2 times z, so 2 by 3 is equal to minus 1. So, this implies y equal to 1 by 3. Okay. And now you have z equal to 1 by 3, y equal to 1 by 3, and so you immediately you look at the first equation. So, x plus 1 by 3 plus 1 by 3 equal to 2 implies x equal to 4 by 3. So, using these row operations, we solved this equation, this system of equations, and without using Kramer's rule or determinants, we managed to solve these equations. And so row operations can be used to solve equations. In a way, we did without using determinants. If you have really large matrices, then calculating determinants each time becomes very tedious, whereas if you do row operations, you can quickly solve the equations. In fact, even to calculate determinants, once you do row operations on a matrix, row operations do not change the determinant. So, now once you get a matrix into this form where you have zeros, okay, then you can see that it is very easy to calculate the determinant. Okay. So, row operations can also used to calculate determinants. So, what you do is you convert this matrix into a form where you have zeros on one side. Okay. So, I will just mention a few more things. So, this is related to the row operations. So, suppose you have a matrix, okay, that looks like this. So, it has zeros on one side. So, it can be an arbitrarily large matrix, but it has zeros on one side of the diagonal. So, this is called the diagonal of the matrix. So, on one side of the diagonal it has zeros, okay, then it is called an upper triangular matrix. Okay. And similarly, if this matrix has zeros on this side of this diagonal, okay, so this is called a lower triangular matrix. And if the matrix has zeros on both sides of the diagonal, so it has zeros here, zeros here, then it is called a diagonal matrix. Okay. And you can see that whether you have a lower triangular, upper triangular or a diagonal matrix, okay, the determinant for each of these matrices equal to product of diagonal elements. So, whether you have an upper triangular, lower triangular or a diagonal matrix. So, whether you have an upper triangular, lower triangular or a diagonal matrix, the determinant of each of these matrices is nothing but the product of the diagonal elements. Okay. Now, a few more things about determinants. Okay. And then we will stop this discussion. So, suppose you have a matrix. So there are properties of determinants. I will just list them and you can show them easily. Okay. So, first one is that if 2 rows or 2 columns of a matrix are identical, determinant is 0. Okay. Also, if one row or column has all elements equal to 0, determinant equal to 0. So, basically if you have a matrix where on an entire row you have a 0. So, for example, if you have a matrix where you have 0, 0, 0, 0 and then you have some non-zero elements A1, 2 and so on, but you have one entire row being 0, then determinant equal to 0. Okay. So, this has determinant equal to 0. Similarly, if you have a matrix where 2 rows or 2 columns are the same, then the determinant is equal to 0. Okay. So, this is one property. The second property is row or column operations leave determinant unchanged. Okay. So, suppose I do these row or column operations that we talked about, then the determinant does not change. The third one, cyclic permutation or interchange of rows and columns leaves determinant unchanged. Okay. So, that means what is a cyclic permutation? I just take any one row or one column and then I sort of shift all the rows and columns by 1. Okay. So, for example, what is a cyclic permutation? So, if you have I will just do one cyclic permutation of row. So, if I have A11, A12 up to A1n and then all the way up to AN1, AN2 up to ANN. Now, if I do a cyclic permutation, so if I take the determinant of this matrix and I imagine doing a cyclic permutation, so this determinant is the same as, now I shift AN1 here, A1n, ANN and then I have A11, A12 up to A1 n minus 1 and all the way up to AN1, AN2 up to AN n minus 1. Okay. So, what I did was I just took this last column and I moved it all the way to the first and I shifted all the columns to the right. Okay. Then the determinant is unchanged. Okay. Now, similarly, if you interchange all the rows and columns, if you swap the rows and columns, that means in other words determinant of A is equal to determinant of A transpose. So, if you swap the rows and columns, then the determinant is unchanged. There is one more rule, I will just mention this briefly, that if you swap any 2 rows or columns, okay. So, if you just swap 2 rows or columns, then the determinant changes sign. Okay. So, if you swap just 2 rows or columns, okay, then the determinant changes sign. Okay. So, this is the last property, I will just write this here. So, swapping any 2 rows or 2 columns changes sign of determinant. Okay, so these are some of the properties of matrices and determinants. Okay, and you can use these to solve equations very quickly. Okay, so you whenever convenient, you swap rows or columns, or you add rows and columns, or you take linear combinations so that your calculations become easy. Okay, so in the next class I will try to do some practice problems. I will do some practice problems on these topics.